organized by the Department of Civil, Structural and Environmental Engineering from our transportation group, the Institute for Sustainable Transportation and Logistics, and the Transportation Informatics University Transportation Center. Thank you all for being here in this Friday afternoon. I'm Panos Anastasopoulos, and it is with great pleasure and great excitement that I'm introducing today to you Professor Summer Madanat for our seminar. Professor Madanat is the Zenel Distinguished Professor of Engineering and the Professor and Chair in the Department of Civil and Environmental Engineering at the University of California, Berkeley. Until recently, he was the director of the Institute for Transportation Studies at UC Berkeley, and he was also the former editor of the ASA Journal of Infrastructure Systems. He served as a chief editor-in-chief for that journal for over a decade, and he was practically the main reason for building the reputation of the journal and making it perhaps the best journal in infrastructure systems engineering. He's currently an associate editor in the European Journal of Transportation and Logistics. This is also a very prestigious journal, and he's serving as editorial board member in several top-tier journals. He has published extensively in the fields of infrastructure systems engineering, in transportation in general, with a focus on statistical and econometric modeling. He has about 100 journal articles in some of the best journals in our field. One example is All Parts Practical of Transportation Research, which are considered practically the holy grail in our field. He has given talks, about 50 talks in the US and across the world, and he has graduated about 24 of PhD students, with many of them holding key positions in academia. One example is Professor Jorge Proger, who is an associate professor at the University of Texas at Austin, and he also has many of his graduates holding key positions in the industry, as for example the World Bank Organization. He has several of them. Professor Madanat, thank you very much for honoring us and being here with us today. With that, the floor is yours. Very much looking forward to your presentation.
Thank you. Thank you very much. Thanks very much for this very generous introduction. I actually was editor-in-chief for just less than a decade, 9 years and a half. So,
still the impact.
Thank you. Thank you. When Professor Adel Saleh asked me to present, I thought that it was, given that this is the Institute for Sustainable Transportation and Logistics, that I talk about some of my own research that is at the intersection of sustainability considerations, primarily having to do with greenhouse gas emissions and energy consumption, together with the field of transportation. And the presentation is probably too long for 1 hour, so but it consists of 2 parts. So I'll try to cut that if I watch myself, and if I say I'm running too long, I'll skip over the second part. So the idea, this is research, first of all, that is with several co-authors. It's a series of dissertations and journal papers. The focus is going to be, that first part really, is on the incorporation of greenhouse gas emission reduction objectives in the context of pavement management, and specifically reducing roughness, pavement roughness. So I'll talk about this, first of all, at the conceptual level. I'll introduce the problem, the simple problem, which is at the facility level. And then then I'll introduce the more realistic problem, which is at the system level, to discuss how this framework and methodology we've developed can be used for policy analysis, And then, if I have time, I'll show the equivalent problem in the planning of urban public transportation systems. Okay. So these are some of the references on the basis of work. So as you can see, some of them have to do primarily with problems of pavement management, and the last couple of these papers are more concerned with the trade-off between life cycle cost and life cycle impacts. So the motivation, I think this is an audience that knows knows a lot about concerns about greenhouse gas emissions. California is probably at the forefront, actually is at the forefront of the states in this country in trying to take very serious steps toward reducing its greenhouse gas emissions. We've had over the past decade an assembly bill, that is the California Assembly Bill 32, which calls for reducing greenhouse gas emissions in California by 2020 back to its 1990 levels. And the governor issued an executive order to take that law and expedite it. The transportation sector worldwide is the third largest emitter of greenhouse gas emissions, but in California it's actually the second, mostly due to the very extensive highway network and the fact that California is both, in addition to automobiles, has two of the biggest ports in the United States, Los Angeles, Long Beach, and Oakland, and therefore very significant truck traffic. These are some statistics about the California road system, but given all of this, that kind of points to the importance of pavement condition. And when we talk about pavement condition, there are many ways that you can measure pavement condition. There are multiple measures of performance, including cracking, rotting. The most important really is roughness. And the most important for two reasons. Primarily because roughness is kind of a result of these other mechanisms that lead eventually to a rougher road. So roughness is the result of increase in cracking, in raveling, in rotting. All of these add up to create rougher roads. Roughness is measured in International Roughness Index units, which are meters per kilometers. And they measure the vertical displacement per travel relative to a perfectly planar surface. And this kind of a flow diagram gives you an idea of how roughness eventually develops as a result of these various other mechanisms. Yeah. Now, roughness is also very important because it is a major driver of vehicle operating costs. By this we mean both wear and tear of vehicles and fuel consumption. So it's for most state agencies in the US and many countries, what they use to drive their pavement management conditions is often the increase in roughness. And so in a very simplistic type of pavement management system, you have two possible alternatives. Doing nothing, which leads to an increase in rolling resistance, fuel economy goes down, wear and tear goes up, and also, importantly, greenhouse gas emissions go up because of the decrease in fuel economy. These are some of the papers based on which we have developed models that we'll be using in this presentation. If you do resurfacing, I don't know why my slides are so. If you do resurfacing, roughness goes down, but of course you have an increase in material and construction costs associated with resurfacing. So typically, the succession of roughness progression and resurfacing actions lead to something like a sawtooth curve, which is typical of roughness progression on a typical highway pavement. So where T is the time axis and S is roughness as measured by IRI. The question, of course, therefore, is when to resurface. At which point should we resurface? And most state highway agencies use something that they call the trigger roughness. So that's the point at which, when roughness reaches it, a resurfacing action is applied. In California, that happens to be 2.7 meters per kilometer. Formerly, they used a trigger roughness of 3.5 meters per kilometer. They've abandoned it about less than a decade ago to this. The Washington State DOT, which is another DOT for which we have a lot of data and we've collaborated with, use a 3.5 meter per kilometer. So there are two questions here that one needs to ask. Are these roughness values optimal? Do they represent an optimal trade-off between user cost and agency cost? And the answer is no. They're basically typically used or determined on the basis of subjective criteria. Kind of, a panel of experts sitting around the room and deciding that this is a good number. The other question is, should you have a single universal trigger roughness for all pavements, for all the pavement segments in your jurisdiction, for example, in the whole state of California? And that is a question worth asking and seeing whether this actually makes sense. So our research objectives here are to develop the framework for optimizing roadway pavement maintenance, specifically overlays, resurfacing, that would take into account both costs, meaning life cycle costs, including user and agency, and emissions, greenhouse gas emissions, coming from both the users and the agency, both at the facility and system levels, and then to use that to do some policy analysis. So some limitations, to keep this research manageable, and also in view of the fact that the limitations of data and models that we have, we're only considering asphalt pavements and overlays. We're not looking at rigid pavements, concrete pavements with overlays. We're excluding minor pavement activities, pavement maintenance activities. These typically have are much smaller in terms of both costs and emissions relative to the resurfacing the pavement. We're not looking at end-of-life considerations. And though roughness may have impacts on other than fuel consumption and wear and tear, for example, damage to goods, California being an agricultural state, and many of these produce being transported by trucks, obviously rougher roads can lead to situations where you end up with tomato paste instead of tomatoes by the end of the trip and other things like that. We're not looking at that. So let's take a look at the entire array of sources which are likely to produce greenhouse gas emissions associated with the pavement. So there are multiple sources, all right? The materials, extraction. So we look at the entire supply chain here of producing the pavement, right? And of operating it and maintaining it. So the materials for construction and for overlays, the transportation of these materials, on-site equipment, traffic delays if you need to close the road associated with an overlay. And then there are several things that have nothing to do with roughness, but that also are possible causes of greenhouse gas emission. And then rolling resistance associated with roughness. Now, you see that the most important, the largest impacts really are these five: materials and construction, traffic delays, and then rolling resistance. Structure is actually not relevant for us. It has to do with the rolling resistance that's due to the structure itself, not to the pavement. So we'll ignore these. In fact, we'll end up looking at just these two. The reason for ignoring traffic delays is that in California, Caltrans's policy is to apply all overlays at night. And for most roads, the impact on traffic, therefore, is minimal. They don't close the road, they close one lane at a time typically, and when you have very light traffic, so they do that after midnight, you have very light traffic and the impact here is insignificant. I'll skip this one for now. So, focusing on the initial problem. So the problem that highway agencies currently deal with, they're interested essentially in minimizing life cycle costs, including both agency and user cost, right? What inputs do they have to make that decision? Well, they have typically a roughness progression model that's been developed using statistical methods, some model or some measure of the effectiveness of applying an overlay in reducing roughness, the unit cost of resurfacing, user cost, and their problem is to essentially determine the frequency of resurfacing, that is, the periods between resurfacings, or equivalently, the trigger roughness. These are the same thing. And the intensity of the resurfacing, that is, how thick, right? So that overlay. The problem is this, so you're interested in determining the S2 here, and S2 could be time varying or could be constant in steady state conditions, and which is the same as determining the time period between this resurfacing and the one before it. So there's a the problem is a formal nonlinear optimization problem where we have the entire life cycle cost. So this is for an infinite planning horizon for a series of cycles, and in each cycle there's a cost associated with the overlay and a cost associated with the users as well. And this is the users rather, and this is the overlay. There's a deterioration function that describes how roughness progresses, some initial conditions and boundary conditions, and for an infinite planning horizon, not surprisingly, you eventually reach steady state conditions, which means that you have to solve for a single S2. So that kind of trigger policy, which is used by state agencies, turns out to be logical. What state agencies typically will do is they will apply a trigger, except that that trigger is subjective, and whenever they overlay to the maximum possible reduction in roughness. So there's a technological upper limit on the size of that drop, because an overlay cannot reduce entirely, cannot bring a pavement to as new conditions. But they apply resurfacing to the maximum possible extent of reduction. I'll skip over this. So we get basically two insights from solving this infinite horizon problem. The first, which I just described, the optimal strategy is to resurface with fixed intensity whenever pavement condition reaches a specific threshold. And it turns out that this solution is quite robust to deterioration model uncertainty. So solving the problem like I did here deterministically is fine for this particular problem, because you can be off in your prediction by up to 20 or 25% with less than a 5% impact on the optimal solution in terms of cost. There's also an equivalent where we solve the problem for finite planning horizon, and this is described in this paper. And we find essentially the same thing, that we do obtain steady state solution except near the end and the beginning of the planning horizon. And it's always it's the same kind of trigger roughness policy, the threshold policy here, that says that whenever you reach a trigger roughness, you should do the maximum possible reduction in intensity. So this is called a threshold policy in dynamic programming and optimal control, and this is really what we have. Again, fairly robust to deterioration model uncertainty. All right, so that's what we did in the context of minimizing life cycle cost. Now let's bring in emissions into the picture. So in the case of emissions, just that of life cycle cost, there is a trade-off between what happens on the agency side and what happens on the user side. So if we look at overlay intervals here on the x-axis, and CO2 emissions per mile in kilogram per year. As you increase the overlay intervals, the roughness emissions are going to increase. That is, those coming from the users, and that's obvious. Your pavements are rougher for longer, and therefore your vehicle fuel consumption increases and your CO2 emissions increase. On the other hand, obviously, the overlay CO2 are going to decrease. They decrease because you're doing fewer overlays and therefore there are fewer materials and construction emissions. And so somewhere, if you look at the total emissions, somewhere there's a sweet spot where, for that particular example here, comes to about 17 years, it looks like, where your total emissions are minimized, right? Now note, though I didn't show a picture for life cycle costs, it's the same thing. If your overlay interval increases, the user cost will go up and the agency cost will go down. So it's the same concept that we have in the case of cost. The difference, of course, is that these optimals don't necessarily coincide. They don't fall at the same value of the overlay interval. So if we have here on the x-axis the overlay interval, we have CO2 emissions on the left, costs on the right. If we look first at the pink curve, this is kind of like the green curve I showed before. This is the total CO2 emissions. This is the total cost, life cycle cost. So we see that in this particular case, for this particular pavement, the optimal overlay interval from the point of view of emissions is around 15 years. The one for to minimize life cycle cost, the optimal value is 30. So obviously being to the left of 15 makes no sense because both things increase as you move to the left of 15. And if you move to the right of 13, both curves increase. So, but you have a span in the middle where it's possible to reduce one at the expense of the other. So we call this an optimal span. And this is the span of interest. This is where the trade-offs exist between cost and emissions. So to formalize this a little bit, we use the concept of a Pareto frontier. And so here you have emissions on the x-axis, cost on the y-axis. And the blue curve here represents the set of optimal solutions. It's called the Pareto frontier. So every point on this curve is optimal, right? In the sense that any point on this curve, if you want to reduce cost, is going to be at the expense of emissions, and vice versa, right? You cannot be below that blue curve, but you can obviously be above the blue curve, which is to do things that are inferior, right? So for this particular two-lane rural road, a specific road in California, District 4, which encompasses the Bay Area where Berkeley is located, it turns out that the Caltrans current policy falls on the Pareto curve. I mean, that's quite remarkable that the state agency here, for this road at least, is able to obtain, or uses a policy that is optimal, right? The previous policies by Caltrans would be above the curve, and this is the one that corresponds to currently Washington State. So this point is obviously inferior because it's possible to obtain a lower cost for the same level of emissions, or lower emissions for the same cost, right? So that's a good example. When I present this research to an audience that has Caltrans engineers, I like to start with this one. Because it makes them look good. Not so much this one. So this is for an actual specific two-lane urban road in District 4. And the Pareto curve is here. And you see it looks very small because we had to increase the scale just to show where Caltrans' policy is. So, I mean, they could reduce effectively their greenhouse gas emissions by more than 50% and reduce their costs by moving from where they are to this point. I mean, they're far off the Pareto curve. Their previous policy was probably equally bad, much worse in terms of cost, though not as bad in terms of emissions. So for this particular road, this is how the Pareto curve looks. The three-lane rural road shown here, again, the Caltrans policy is practically on the Pareto curve. I mean, if you extend this, so after that blue line becomes horizontal, right? That is the constraint on emissions stop to be binding, right? So it becomes horizontal. So you can see that the Caltrans policy for rural roads actually works out quite well. It doesn't work very well on urban roads. Again, same picture here. With big potential for reducing emissions. So this is for specific roads. This is not the problem that Caltrans solves. It doesn't solve maintenance policies for one road at a time. It needs to balance, or rather it needs to allocate its budget, a fixed budget, financial budget, across an entire network of highway pavements. And so what we're going to look at here is first the solution for solving the system level optimization, and then we'll again introduce greenhouse gas emissions. So rather than kind of fill the screen with mathematical formulations, I want to first try to explain conceptually how we solve this problem at the system level. Right? So what we do is what is called a bottom-up solution. So we start by solving optimal solutions for individual pavements. All right? And then when we impose a budget constraint, we modify these optimal solutions by effectively changing the optimal threshold. That's kind of a caricature of the solution. And it's a resource allocation problem. So formally, we're minimizing annual agency and user costs, subject to, in steady state, having the agency cost be below the budget, below or equal to the budget. So here you have capital N segments for which we're doing resurfacing. And what you're seeing here essentially are different pavement segments with different optimal thresholds. So some of them get resurfaced very rarely, some of them very frequently, and anything. So now, corresponding to these sawtooth curves, we have cash flow diagrams associated with them, right? So the idea here is that the big arrows represent the resurfacing, the small arrows represent the user cost between the resurfacing. And the user cost is supposed to increase, but this is just a simplification. So now if you add up all these costs on a year, if you add up these curves essentially vertically, you're going to get a cash flow diagram associated with the network as a whole, with the system as a whole, and it might look like this. The problem, of course, is that your budget is never going to be high enough to do everything you want to do in most years. So because the budget is lower, then you're going to have to modify your thresholds here in such a way that in the steady state you're using the whole budget, but nothing more. So I won't show the math formulation, but it's described in this paper, Satya and Madanat. And this is what we get for, and this is for several hundred pavement segments in District 4, so it's a representative sample of the problem that Caltrans district have to solve. So what am I showing here? I'm showing on the x-axis the budget per year and the trigger roughness on the y-axis. Then the different colors here of the different densities are in fact representation of the number of pavement segments which have, at a given level of budget, that particular trigger, optimal trigger roughness. So dark regions mean that there's nothing there. There's like no pavement segments, right, in that region. And the light ones mean there's a. So that you can think of these as probability density functions. Take a cut like this at, for example, 30. This is, and you look at it, this is like a PDF of pavement segments distribution, right? And here's what we see. Well, the first thing we see, which is kind of obvious, doesn't take research to do, is as we increase the budget, we can do many more resurfacings at the optimal time. In fact, the trigger roughness, on average, all the trigger roughnesses are going to go down. That's how. But the other important thing, which is very critical, is that this is not a line, it's an entire PDF. So that policy that most state DOTs, in fact all state DOTs that I know of, and most countries have, which is to use one trigger roughness for all their pavements, is really not a good idea, right? That you can see that, you know, taking for example here, this particular budget, the distribution of trigger roughnesses goes everywhere from 1 IRI to 3.5 IRI. So you know, this is a very big range of trigger roughnesses. And using just a single one, let's say 2.7, which is what Caltrans uses now, 2.7 somewhere here, as a trigger roughness for all their pavement segments, clearly doesn't make sense. So that's what I just said, written again for emphasis. And then, again, though I'm not showing this, the optimal solution turns out to be quite robust to deterioration model of certainty. That is the roughness progression model. So now let's bring in life cycle emissions into the picture. And there are two ways of thinking about this problem. One of them, which corresponds more to the situation in California, where the state has told agencies they need to be at that particular level of budget of greenhouse gas emissions. And so Caltrans has, as a result, to meet a certain target, right? So what Caltrans would be doing is to try to minimize life cycle costs subject to the constraints on their greenhouse gas emissions. So the problem turns out to look like this mathematically. So these are the costs, and this is the emissions constraint, which would be, it's like a budget. This is how much you're allowed to emit. And again, we're going to, so we'll be able to use this to draw a Pareto frontier. So this is Caltrans District 4, not the entire district, but the representative pavement sample. And again, the picture doesn't look good at all for Caltrans. This is the Pareto curve, and we had to shrink it just so that we could show both where the current Caltrans policy falls relative to it, as well as the previous Caltrans policy. But at the very least, there's progress. Right? There's significant progress moving from here to here. But there's about an equal amount of progress would be needed just to get to the very rightmost point on our Pareto curve. In other words, the point where the costs are minimized. Okay? This is the lowest. And by moving from the current 2.7 meter per kilometer trigger roughness to the distribution of optimal trigger roughnesses for this network, it would reduce both costs significantly and emissions probably even more significantly. So this is quite telling. Now, one thing that those of you who are familiar with Pareto frontiers have probably already deduced, or you must be asking, is, well, can't we use this to come up with an estimate of the carbon price that a certain state or country uses? Now, obviously, the slope of the Pareto frontier at any point is the price of carbon at that point. So different points represent different trigger roughnesses, right? And so if you're here, for example, if you decide that this is the point on the Pareto frontier where you want to operate and have a certain trigger roughness associated with that, or distribution of trigger roughnesses, then the price of carbon is the slope. And that's obvious because the units of the slope of the tangent are dollars per metric ton of carbon. So, which is the price of carbon, right? So, Caltrans has started doing carbon auctions, and the price that they obtained in the last carbon auction was about, I believe, close to $10 per metric ton of carbon. And so that would be here. So if, according to that, for that particular price, Caltrans should be on this point, on the Pareto frontier, and that would dictate then the trigger roughnesses and the time period between resurfacing. Study by Nittel and others came up with a different approach to the price of carbon, which in their opinion should be closer to 100. So 100 would bring, all right, still very much towards the right of that Pareto curve. So that's kind of on the other hand, so I mean that would be like a market price, if you will, in the case of Caltrans, California. If on the other hand society decided that this is more what it's willing to pay for reduction of 1 metric ton, then it would impose it here, and this is the free operate. Now the other things we can do, Caltrans uses different practices for resurfacing. One of them is to resurface the entire, all the lanes on a highway when the rightmost lane, which carries the most trucks, reaches a roughness of 2.7 meter per kilometer. And these are the results I showed before. The other one is to just resurface that particular lane. So that obviously reduces both costs and greenhouse gas emissions. And so you see the curve now, that becomes much closer to the curve. So that policy obviously makes more sense. If through technological improvements we could make the application of overlays lead to a lower roughness, for example, we've looked at a case, there's a curve missing here. But in any case, maybe if we just show these two, you see that if you're able to reduce roughness more as a result of the application of overlay, your entire Pareto frontier shifts towards the left, which has both cost and emissions implication. VMT, obviously, you reduce vehicle miles traveled. As a result, your Pareto frontier also moves to the left. So this is the base case. This is a 20% reduction in VMT. There are very significant reductions both in greenhouse gas and cost for any point on the Pareto frontier. So let me see if I'm going to present this. I'm supposed to end at 3.
Yeah, we can.
No, maybe I'll skip this and kind of show you. So this is simply a different perspective. Instead of minimizing greenhouse gas emissions subject to the budget constraint, here we have a situation where instead you're trying to minimize greenhouse gas emission subject to a particular budget, financial budget. So I'll skip over this. Instead, kind of show the equivalent problem in the design of urban transit networks. Now, in order to kind of frame the question, it's going to be this. It's like if a city were now to design an urban public transport network to essentially using the objectives that cities currently have, which is to some kind of minimization of total societal costs, meaning the travel times and waiting times on the user side, as well as the cost to the agency of operating and maintaining its fleet and its infrastructure. So how would their policy change? So there are many ways that people have tried to solve that kind of the optimal design, the optimal network design for urban public transportation system. Many are very detailed and use some very, very complex at times and computationally expensive discrete optimization methods. And others are using a continuum approximation method. The idea of a continuum approximation is you basically assume that your city is a plane, to forget about the presence where the streets really are. And you think of your demand as being a density function over that plane instead of specific origin destination demands. So that's the continuum approximation. This kind of approach is very useful for doing two things. First of all, you're able to obtain analytical expressions which connect the causes, right? So the causes in this case being the design criteria, the design quantities that you're solving for, which is spacing between lines, spacing between stops, frequency of service, and the effect, which are costs, societal costs. So that, is no longer a black box optimization, but something very clear, and therefore that clear relation between cause and effect allows you first to explain this to decision makers in a simple way. And the other thing it does is it allows you to modify, to kind of play with the causes, see how the effect comes up, so that you can yourself do a lot of sensitivity analysis. The third thing is that solution is very quick, right? You're using basically the tools of calculus, essentially nonlinear cost minimization. What you get are obviously not the final optimal solution, but they get you very close to the final optimal solution. If you then want to introduce the street network exactly, and where the nodes and the intersections and links are, you can then search in a narrower space. Or you can use these and then try to modify the optimal solution by hand, essentially, to fit where your transit lines are and where your stops are relative to the actual street network. So this is for a bus network, for example. For metro, it's not even necessary. So, so this is what we decided to use, and because our objective is to obtain kind of these general insights rather than exact, precise solution. And there's a paper here that describes this at the bottom. So we avoid the need, as I said, for computation expensive discrete optimization, and we obtain near optimal solutions, I said that. So if you take kind of a grid network for a bus system, the solution, the three design quantities are essentially the spacing between the lines, both in the Y direction and the X direction, the spacing between the stops, this is for buses, right? And then the frequency of service, that is the headway, the time between the arrival of two consecutive buses at a given point, like a particular station. So, when we want to introduce emissions into the picture, this is in fact the solution, the problem we're solving. We're minimizing the sum of user costs, which are essentially time, and agency costs, such that the emissions is less than a particular emission constraint. Another obvious, for realism, you need to make sure that the load on any given bus is less than the capacity of the bus. These are the three decision variables: headway, route spacing factor, and stop spacing. In effect, the P works with the S to give us the final route spacing. Right? The idea is you have multiples of stop spacings that give you route spacing in the other direction. This is the transit network structure, so this is where you see P times S. These are the parameters of interest: the demand density, the length of the urban area, the width of the urban area, so we're assuming a rectangular city here for simplicity, with the grid network, as I said. User access P, that is the access from wherever the person is to the bus, because that's access time, it's part of the user time, and the user value of time, okay, which is kind of a representation of, as unit dollar per hour, is how how does a user make the trade-off between time and out-of-pocket cost. Some people have usually used wage rate as a way of obtaining that, but there are a bit more accurate methods. And typically, in reality, you should have more than one user value of time. You should have the value of time is different when you're on the bus rather than waiting by a factor of 2 or 3. So for realism, in the later work, we had 2 or 3 different user values. So this is the user cost, this is the agency cost. I won't go through it, just to say that it includes the cost of access and egress, the cost of waiting and transferring if they need to transfer between a line and another, and the in-vehicle travel time. For the agency, there's the cost of the infrastructure itself, the vehicles, purchase and maintenance, labor, and the cost of the station. All right? And we looked at 4 possible scenarios. We created these synthetic cities, really, toy cities. Some are small, some are large. So we made them square to simplify life even further for ourselves. So they can be 10 by 10 or 40 by 40. The demand density can be low, like 100 passenger per square kilometer per hour, or high, 200. Now notice this is density, we're not differentiating between origin and destination, right? It's the same thing. The wage rates, it can be a poor city or a richer city, and so that gives us an idea of the value of time. And this factor actually combines mu and delta into a single factor because they can be combined. Now, the technologies we're looking at include everything from buses to bus rapid transit, BRT, light rail transit, and metro. And they have speeds, costs for right-of-way, costs for maintenance, emission factors, etc. So the constraints are the emission constraints and the capacity constraint, bus capacity. And this now the problem is posed, right? We have a particular city scenario, particular mode, particular constraints on both greenhouse gas emissions and capacity. We have this nonlinear minimization problem, and we obtain some decision variables, which are the spacing and the head speed. So just for, and these essentially come from these particular values of total cost. So if we start with no, so for this city, for this mode, with no constraint, we obtain a point on the Pareto frontier. So again, this is emissions X and cost Y. And this is the point that we get if we don't impose any constraint. Then we repeat that with by changing to a particular constraint, a low constraint, we get a new point, and another one, etc., etc. You get the drift, and so we end up with a curve like this. Okay. So this is for particular mode, which is metro here, a particular network, a particular scenario, combination of city size and wage rate and demand density. And so we get this Pareto frontier, and that helps us guide, or helps guide us depending on where the city considers the appropriate price of carbon. If it's here, that gives you a particular spacing, headway, and stop spacing, or station spacing, that it should design eventually. And we can do this for all kinds of cities. So here, low demand, small city, for the 4 modes. And so you see some results that are interesting. For example, yes, bus is in a low demand small city has a lower cost, but at its cost optimal point, it produces higher greenhouse gas emissions than BRT, whether it's a low wage city or a high wage city. All right, and then here we increase the demand. Now BRT and bus have almost equal total cost, societal cost, right? Then you go back to low demand, but you increase the size of the city, so that's about the same as what we had. And then when you go for a high demand large city, then everything changes. Bus becomes the most expensive mode, in fact, in terms of total cost, whereas metro, for example, becomes the second best in terms of cost, but it's quite high in terms of greenhouse gas emissions in general. So BRT, things like BRT happen to be the best. There are all kinds of simplifications we've made here, obviously. This is not meant to be kind of something a city would use tomorrow, but it kind of gives insights about the trade-off between these attributes. For example, one thing we assumed here is that demand was inelastic. So we can reduce the level of service, by moving to the left here, right? Increasing costs. When you reduce level of service, it's the user costs that go up. The agency costs actually go down, but the emissions as a whole go down because the emissions in the case of transit are only associated with the agency. I mean, we're not counting the greenhouse gas emissions that individuals may count on their. So we allocate the entire emissions to the transit, to the bus or the metro. But if demand elastic is large, then trying to reduce greenhouse gases by, for example, moving from the cost optimum point in that direction, since we're assuming cities, if they're doing their work right, are going to be close to this point, right? But if they want to reduce greenhouse gas emissions, initially they may reduce the level of service, increase the cost a little bit, and nothing will happen. But if they go too far, you're going to end up with unintended consequences, that people are going to shift from bus to more polluting modes. So this is something that we need to also be careful. And this is in fact what we're trying to say, is that if sufficiently large, the mode shift may lead to an increase in the total footprint of the urban area, because people are going to now, we're assuming for simplicity, move to driving alone, right? Therefore, while the transit emissions may go down, the total city emissions will go up. And so we've looked at some of that, and that can in fact happen. So this is for light rail transit. And we're showing here from the cost optimal point. So this was here we have transit travel time and emissions. These are the axes. So this point corresponds to the point that was the cost optimal point at the right end of the parity frontier. And now we're going to increase the travel time. So if the users are inelastic, as we initially assume, well, that's great, because basically you stick it to the users, but you reduce your carbon footprint. But for the users are more elastic, their demand is elastic, then what we're going to see is that maybe you'll have initially some reduction, but then finally, for high values of transit travel time, you end up with higher carbon footprint. So that's the kind of unintended consequences one needs to be aware of. Some limitations, we had the grid network, we had uniform demand density. We didn't take into account kind of hierarchical trunk feeder system. We're assuming people walk to the stations. So this is partly why metro turned out to be always so high cost, is because in a high city, high demand cities with high wage rates, right? You're going to, the metro is expensive, so you typically would want to keep it as far as possible. But if the user costs are high, you want to bring it closer to each other. Now, in reality, in most cities, you have buses or some other modes that take you to the front line, those feeders. So we did take this into account. And again, with assumption of that. So, on time, I guess. So thank you. I'd be happy to answer any questions.
Do you have some of your slides available to share with them from a transit advocacy group? And one of the big debates in this community is the cost of expanding our metro line, and what the benefits might be versus the cost. It seems like this research would be very useful.
Certainly. So, first of all these slides for the transit and many others that I didn't show are published in one paper, which I think I showed earlier. So this paper is in Environmental Research Letters. It's Griswold, Madanat, and Horvath. So Griswold was a former PhD student of ours, and Arpad Horvath is a colleague at UC Berkeley who specializes in life cycle accounting and greenhouse gas accounting. There's a subsequent paper to this one that's under review, kind of final review, that will come out that shows the effect of accounting for elasticity. So more realistic system by the same author. For pavements, we have this, and there's actually one that just came out. So the other Griswold paper is also in the Environmental Research Letters. So you see what I showed here and much more. Other questions?
So some of the previous teachers has shown that pavement performance has effect on safety. So while considering your cost or finding the trigger IRA value or roughness value, have you considered any of the safety perspective?
No, so safety comes into there are two effects. One is skid resistance, right? The skid resistance is at the level of that is not captured by the roughness, right? So the microtexture of the pavement surface and how the tires interact with it in situations of braking with or without the presence of water. But that's not included. So anything we're doing here with roughness has in fact no effect on safety.
Okay.
The only thing where it could is that part of roughness comes from rotting, and rotting is what typically is caused by trucks, where if you look at a road segment, kind of as if you're facing traffic, the pavement may have kind of these, the depressions, and that contributes to roughness. So while we didn't account for it, but certainly it's part of the roughness. So it's not, we didn't explicitly account for costs of accidents, of crashes, and lives lost or anything like that. That wasn't part of the objective.
I have one question.
Please.
From your work, you have showed that like one trigger roughness is not good for network. But like, have you checked that doing the rehabilitation individual lanes has actually performed better rather than the network-wise rehabilitation?
Lanes or links? I mean,
Lanes, like you say that.
Yes. Yeah. So in terms of performance, it's optimal in the sense that it minimizes the sum of the discounted agency and user cost over a long planning horizon. So if some pavements are going to be resurfaced less often, and the trigger roughness for them will be higher than 2.7, and others will be the optimal solution will say should be resurfaced more often, should have a lower trigger roughness. Now though I didn't show it here, we have collaborators at UC Davis who basically took these results and tried to, instead of finding individual trigger roughness for individual segments, which from a kind of practical perspective is not easy, they've basically taken our results and classified them into bins. And what they show, not surprisingly, is that the segments that carry the highest traffic are the ones that should be resurfaced more often. And the ones, so if you take our entire distribution and you divide it into 4 bins, approximately, the highest traffic one, for I don't remember which budget constraint, had resurfacing trigger roughness of 1.5 meter per kilometer, which is extremely low. But this is, like for an interstate, like I-80 or 580, basically the major interstates in the Bay. Whereas kind of some of the roads which are local roads carry much less traffic, the trigger roughness was as high as 4. And in some cases, they recommended that some of them we never resurface. And in fact, because the progression is so slow that other problems are going to happen before you need to do anything for roughness. Right? So for example, cracking may become excessive without causing a lot of roughness, but you cannot allow this amount of cracking. For example.
Is there any reason you only consider CO2 in your emission? You don't consider
CO2 equivalent.
CO2 equivalent. You
Yeah,
convert to CO2.
maybe it wasn't clear. It's really CO2 equivalent.
Okay.
So,
And out of curiosity, what is your deterioration model for pavement toughness?
So
It's kind of non-linear curve, right?
yeah, it's
And
non-linear, right? And which is so there we've used different ones in different files. So for example, here we used something very simple. We were comparing our work back in 2002 with that of a group of researchers at another university. And so we used their exact deterioration model, which is quite simplistic. It's kind of memoryless. It's Markovian in that sense, exponential, nothing really exact. As we moved further and further away, here we started using more memory, so history-dependent models, in particular here. And so we looked at, there's a model developed by Bill Patterson of the World Bank that was developed about 15 years ago or so. That is very realistic in that it accounts for structural number, the thickness of the pavement, for the amount of easels, equivalent single axle loads, the effect of environmental considerations, at least precipitation. So we adapted it, and that's what we use here and also in this paper.
Do you consider how many weight you travel on the pavement?
Yeah, the easels, the equivalent single axle load, which is a unified measure of so for those who are not pavement engineers, so there's a standard axle load is 80 kilonewton, 18,000 pounds. And if you have an axle that carries more than that, let's say double that, then you take the weight of that carried by axle divided by 80 kilonewton and raise it to the power of 4, which is kind of the industry accepted practice, and that gives you the effect of contract.
Another question is,
Yeah, I'm sorry, on the pavement.
so on the continuing approximation methods, you said that you're basically modeling density of demand.
Yeah.
So how do you model the OD where people
We don't.
You don't model OD?
No. Essentially, we're saying that demand is uniformly distributed in terms of origins, destinations, and the average strip length is kind of the average of all possible distances in a grid network, right? So you take the maximum in a rectangle, and you take 0, the average is that. And the distribution of strip length is some distribution that comes from the dimensions of the rectangle. So there's no OD representation, and that's the whole advantage of this continuum method, is you forget about points and links, and you think of this as a surface. You obtain an optimal solution, and then you map that solution to the actual street network, so you need to maybe push things a little bit to the right or to the left, or increase them a little bit later. And so, as I said, you don't get the truly optimal solution, but you get something that hopefully is not too far. One of the things about continuum approximation methods, which is very powerful, is that the objective function at optimality is fairly flat. So you can be, again, just like in the pavement example, you can be wrong by 20% in terms of your solution, but in terms of the dimensions of the problem, the input, but in terms of optimal solution,
It's robust.
It's robust, yeah. So if you want to remember, we didn't invent continuum methods. These really are described very well in the book by D'Aganto on logistics. So that's a good way of learning about that. Yeah.
I was just wondering, so what is the typical impact of the pavement conditions, such as roughness, on this greenhouse gas emissions produced by vehicles?
Right.
Do you have some kind of value range to just give us an idea?
Yeah. So the input into that, because that changes the per unit of IRI, how much increase, percentage increase. And I'm ashamed to say I don't remember the precise number, but it is, I would say, I'll show, you see that reference, Santero and Horvath, 2010. I think it's in, I'm not sure which journal. It's either Environmental Science and Technology or I think it is ESNT. Has a description of kind of the effect of each of these on greenhouse gas emissions per unit, right? Rather than just these total quantities. So instead of trying to remember, I think it's best that I point you in the right direction. But it's significant in the sense that, roughness is the biggest contributor to greenhouse gas emissions, right? So it's a very big deal from the point of view. If you're interested in having an impact through maintenance, through road condition, on roughness, there are all these things where, there's albedo and stuff, but they're nothing compared. Notice this is a logarithmic scale. Right, I forgot to emphasize this. So, so this is 10 times, it's about what? If you compare that to albedo, it's about 100 times more important.
Are there any other questions?
Well,
So in your first portion, you have mentioned that you have considered only asphalt type of pavement and overlay type of pavement. So
and asphalt overlay. So asphalt overlays on asphalt.
is there any reason for selecting only this one?
Well, the other solution is asphalt overlays on concrete pavement, right? We have much better models of roughness progression for asphalt than we have for concrete.
Okay.
So for concrete, neither the literature nor our own research has produced anything really solid enough. So whereas for asphalt, there are, as I described earlier, several models, including Patterson's work. I also did some work with Jorge Frozzi, whom Panos earlier mentioned, who's now in Texas. Our model turned out to be too complicated, requiring too many inputs to be used in this research.
So that's the system of unrelated inflation equations?
This is the, no, this is the one where we developed a roughness model by combining experimental and field data.
Oh, all right.
So that's back 2003, yeah, 2007.
So, Professor Madanat, thank you very much for
Thank you very much.
giving this very interesting and informative presentation.